Welcome, guys. We are Gatorloop, based from the University of Florida. My name is Caden Steffen. I'm the Brake Sub Team Lead, and we're gonna give you a rundown of our previous version of our pod, TinyPod, which we are wrapping up. Like I said, we'll give you a quick overview and then progress on our electrical subsystem, and then we'll also give an insight into our next project that we're working on, which is upscaling this previous version of the pod. So we will start off with our mechanical subsystems, and first off, powertrain.
Hi, so I'm Daniel Woras. I am powertrain sub-team lead, and the previous generation what we had was basically just a brushless motor with a wheel to propel the system. So as you can see in the CAD drawing or CADs above, you can see the general structure of how we designed the powertrain subsystem. And then you could actually the brushless motors with the wheels attached to it. So that's the main system that we had to propel it. So to make sure that the wheels were always in contact, we also made sure to add basically what we decided to call a constant friction applier. So what we call the under friction system, which you could see the little wheels with the spring system there. What it basically did is I made sure that the wheels that were actually being propelled by the motor were always under constant contact with the I-beam. So it always kept that pressure to make sure that we always had that constant friction so we wouldn't slide uncontrollably. Another thing that we also decided to do is that instead of just using the two motors, we actually had a 4x4 propulsion system, which inherently provided a more stable system for the entire pod and allowed us to accelerate much more quickly while also keeping that stability of the system. We could also actively play around with the feed or the current for each motor, so we could also kind of play around with stability in that sense. But this is basically the overarching idea of what we had for the propulsion system last year. So another thing, we also made sure to separate the propulsion system from the main structure. You can see that they're actually being the powertrain system is not connected to the main structure to basically allow for stability to be implemented to avoid any possible vibration that could go into the main structure.
Hi, I'm Roger Montenegro. I'm the stability sub-team lead. So here's a breakdown of the lateral and vertical suspension system for TinyPod. So I'll start with the lateral, which are the two top pictures right there. And we utilized an extension spring system with a pivot control arm to ensure that the TinyPod was centered on the I-beam throughout its travel. And as you can see on the left, we used a FEA to try to optimize the design, but there was not much to improve there. Now with the vertical suspension system, as Daniel mentioned, we had the powertrain motor and wheels separate from the main structure. So we utilized, again, a pivot control arm with a shock in pair with that to be able to dampen out any forces or vibrations that may occur throughout its travel. And one thing that isn't really noted here is that the final product for the pivot control arms for the vertical suspension system ended up having less material towards the middle after utilizing some FEA on the structure to make sure that we were using the least amount of material. But that was basically the basic concepts that we tried to use on TinyPod's suspension system.
Our next subsystem is brakes. So I'm Caden Steffen. I am the brake sub-team lead. Basic overview of our braking system, which you can see there on the right. It's a pneumatic braking system that utilizes a paintball tank that is housed on the top of TinyPod. We used a flange braking design with two brake pads on each side that you can see up in the top right image. The brake system itself utilized aluminum brake lines with flared fittings, and we have a series of solenoids, pressure sensors, pressure relief valves, and other various fittings, which basically allow us to monitor the pressure of our system and autonomously control it through our electrical subsystem, which we will dive into later. So I'll pass it off to structures.
Yeah, so I'm Abigail. I'm the structures lead for Gatorloop. So for TinyPod, the dimensions were just 3.5 feet times 7 inches and then 0.25 inches. The main material was aluminum, and it was just basically different plates and bolted together. So it was really all the manufacturing processes were just milling, drilling, and a lot of the plates were made using the water jet, in the university. The good things of a TinyPod is that it was really easy to assemble. It allowed for really fast modifications, and especially in the manufacturing, the time was regarding time, it was fast. The not so good things is that there was not much space for some of the electrical components, and that the weight distribution was affecting the deflection of the middle plate. But yeah, that's it.
All right, we'll jump into our electrical subsystems now for TinyPod.
Hello, my name is Devin Dykstra. I'm the Sensor and Systems lead. I'll be talking for Antonio because he was not able to make it. Our battery system uses 2 separate packs made up of 41 individual cells. The main one is 10S4P for the motors and the high power systems, and then the rest of the electronics run off of a single battery, just 1S1P, which is plenty for controlling the computers and the wireless communications stuff. The first version of our pack, as you can see pictured on the right, is just connected via copper foil, and I know this is not standard practice because it does limit how much current we can pull from it, but it does allow us to test things and very easily reconfigure the pack, which is why we're doing it mathematically. Or we did check that out to run safely 20 amps. It can probably do more, but we're limiting it to 20 amps. And the next steps would be to actually mount it to the pod and integrate a BMS for safe operation during when we're actually driving. Okay, and then sensor and systems, which is my actual subteam. We take a variety of sensor inputs into a TNC 4.1 microcontroller, and then control the motors, solenoids, and LEDs appropriately. So we use an HC12 chip for the wireless module, which is a 400 megahertz transmitter. It's very low power, which means we can put it pretty much anywhere. And then also, since it's 400 megahertz, we're sacrificing transport speed for range, which is a good trade-off in our opinion, because we're not sending that much data, it's just telemetry. And then also we have a logging system on board. So we have an SD card that we're just constantly writing to. So if anything does go wrong at any point, we're not relying exclusively on the wireless communication to log things. We also have local logging. So what other sensors do we have? 2 pressure sensors for the braking system. The VESC, we're using that VESC just because it's a very well-documented standard for the speed controllers. It gives a bunch of data on the temperature of the motors, the speed, the power going through it, all that. We're using an IMU to verify that the pod is actually moving how it's supposed to, so whether the acceleration matches our motor inputs, and of course if there's any lateral movement that exceeds our thresholds, then we automatically shut off and go to an emergency state. And then the ground station is just a computer with UART commands, an e-stop and a dial to control the speed. So yeah, that's the sensor systems. And the next steps for that would be BMS control, kind of going into the battery. And then right now we're just running off a breadboard, but in theory we can probably make things a bit neater. Maybe a perf board, maybe a custom PCB, we'll see. Yeah, thank you.
All right, sweet. So yeah, like I previously stated, that was our old pod that we've been working on the past few years, and all of our mechanical subsystems are wrapped up for that, and we're finishing our electrical. So currently, what our mechanical subsystems are working on is our next version of the pod, which we are calling medium pod. So yeah, we will go back into our mechanical subsystems to just kind of give you an insight into what we're working on and the ideas for our design.
Yeah, so back to me. So powertrain, what are we doing differently this time around? So we are keeping what we previously had, the brushless motor propulsion system, but the main purpose of that is because we're switching over to linear induction motors, which, if in case you don't know, is just we propel the system by playing around with the electromagnets and inducing current into the actual I-beam to propel the entire system to move forward. The issue that we're mainly trying to solve is that if we want to go higher speeds, then the best solution would be to actually use LIMs. So to get that initial speed, we're going to be using that brushless propulsion system with the wheels. And then what we're going to plan on doing is actually retracting those wheels upwards, letting the pod sit on these vertical stability wheels that we're designing, and then just letting the LIM do the rest of the propulsion that we need. So we're currently in the R&D stage of the powertrain for the LIM. So what we're currently focusing on is trying to figure out how to best approach mounting the LIM onto it, how we're gonna figure out the hybrid system between using the brushless propulsion system and the actual LIM, and making sure that we can maintain that stability in the entire system as we accelerate on. So we're mainly focusing on, as well as using off-the-shelf LIM components to reduce R&D that we might need. So we're mainly looking at using an H2W high-tech LIM that they're offering, and we've been communicating with them, getting some research and documentation that they have for us to basically avoid that extra R&D, as I previously mentioned, and just generally trying to figure out how best to approach the structural problem of retracting the brushless motor train while it's still under load. So we could go on to the next page. So what we currently have progress-wise is we've actually reviewed the horizontal vertical stability, the linear induction motor mounting system, and the lower structure sandwich, as well as the brushless motor propulsion system. We've done all the system requirement reviews, just trying to figure out what are the main objectives that we have to do for the actual project to work. And then we moved on to actually doing a decision matrix, figuring out which idea, which approach is most appropriate to actually meet those requirements that we have for that task. So as for decision matrix review, we've already covered the horizontal vertical stability, LIM mounting, as well as brushless propulsion system. So all those teams are already moving on to the design phase, being headed by 2 or 3 engineers for each division. So hopefully we should have a final CAD model sometime around January to early February, which we'd be more than happy to show at that time. But yeah, that's current progress with powertrain.
So for stability, as Daniel mentioned, we have some new requirements with the LIM being implemented, especially for the vertical suspension. So for the lateral, we decided that it performed very well for TinyPod, and we can have a similar structure in terms of like what type of concepts and designs we can apply for the lateral to maintain it centered on the I-beam. But for the vertical suspension, with having to have a certain clearance for the LIM at all moments, we are going with an approach similar to the top picture and the top right, and making sure that we can always have a certain amount of distance between the LIM and the track. So right now we're currently focusing on researching and developing something that could allow for that to happen at all times. We're spending a lot of time collaborating with the powertrain system or sub-team to ensure that we can implement our stability system with their system as well. So as previously mentioned for TinyPod, it was separate. This time, everything will be together into one structure. So we are spending a lot of time working on how we can implement things together and not have it separate as last time. And most of our research has been around how motorcycles set up their suspension systems, as it is a similar design this time compared to what was done last time. But other than that, we are starting the CAD for the vertical suspension system and allowing other engineers to work on the lateral suspension system and trying to redesign it to have similar concepts, but just be a bigger version to be able to sustain the larger braking forces that will be like present for a medium pod.
Sweet. Yeah, so moving on to brakes. So quick overview. The new braking system actually began designing 6 months ago. During manufacturing of our TinyPod braking system, we realized we had a lot of reliability issues and some issues with actually the effectiveness of the braking system. So we got a head start on redesigning our braking system, which you can see on the right. So this new braking system, it is still a pneumatic braking system that utilizes the same paintball tank, but this time we designed the system to brake on the web of the I-beam. We did this because, one, it would allow us to utilize less brake housings, and also by braking on the web, we figured it'd create more stability for the pod and also Like I said, with the reliability before, when we were braking on the flange, sometimes we'd have more applied force from like the top brake pad than the bottom, which made some instability issues with the pod. This new system also utilizes copper brake lines and Eurolock fittings, which are just easier to assemble and manufacture. And it utilizes the same solenoids, pressure regulators, and pressure sensors as before to control the system. So the key differences between the two designs, which the new one's on the top right and the old one is on the bottom right, is that this time the brake force is being applied by a spring instead of the pneumatics itself. So previously we used the pneumatics to extend the brake pad and brake the pod. This time we're using the spring to brake the pod and the pneumatics to actually retract it. So that way, if there's any sort of pressure leakage, our pod will automatically apply the brake pads to the I-beam. And then another key difference is previously we manufactured our own brake pads, but this time we bought some commercially available off-the-shelf brake pads and designed a fixture that attaches to our system, which you can see in one of the top right pictures. And then also what we did is we adopted a single piston design, which basically simplifies the geometry of the brake housing, and we added two torsional rods, which prevents torsion of the brake pads, whereas before we just used two different pistons, which we had some reliability issues with. So as far as the progress of our system, we've actually fully assembled and tested one of these brake housings over on the right here. And we've got some numbers for operating pressure and our estimated brake forces and frictional forces, which once we get a mass of the new pod, hopefully equates to a braking deceleration of around 1G was our goal when designing this. And yeah, as far as long-term innovations, once we complete this new iteration of the basic pneumatic system, we have started some research on eddy current braking. And if we decide that there is enough room and capability on this new pod, we have considered adding an air compressor to replace the paintball air tanks. So that way our system could basically run forever, theoretically. Pass it on to structures.
So for structures, as we are scaling up the pod, it's not feasible to have a solid plate on top because it's a lot of weight. So instead, we have decided to just use frames and just like have a lot of hollow spaces. Right now, the frame is made of aluminum, and we just have a bunch of attachments for the other subsystems. However, we are trying to do some research on like carbon fiber composites to replace some of the plates and attachments that we have right now in the pod, and to replace it with like carbon fiber plates to just make the whole pod like more light weight. And then we have two levels. The first level is the main level where most of the subsystems are attached with the frame, and then we have a second level which is just made out of carbon fiber, where some of the extra electronics are gonna go, or just like extra things. And then for the aeroshell, we're still doing research on the aerodynamics and which tools and softwares we have to use for that. So that's a work in progress. And we're just doing a lot of research with just how to manufacture, how to incorporate the carbon fiber composites together with some metals, especially for bolting some of the parts. Yeah, so so those are the main changes.
Sweet. So that covers everything from us. Hope you guys enjoyed, and we are now open to questions.
Yeah, thank you, Gatorloop, for a really great presentation. So again, if there's any questions, you can either raise your hand.
From Alex, how have you found your pressure loss due to leaks with these new fittings? Would you guys like to answer that question, or?
Yeah, I can answer that real quick. Yeah, so previously with our flare fittings, we found that it was super inconsistent when we mounted them, because you had to basically mount them like straight on. And we had a lot of pressure leakage with that system. But with our new system, during full engagement or full retraction, we have a lot less leakage, and we're able to basically sustain our brakes being open, I guess, for around a minute at this point. So there is still some pressure loss, but we're operating at such a low pressure that our air tank will be able to sustain at this point for 2 to 3 hours. So yeah, the new fittings are doing a lot better.
We have more follow-up from Alex, other Alex. And what pressure did you say your air tank was at? Question mark.
Yeah, so our air tank stores up to, yeah, I'm sorry, doing the unit conversions right now. So our operating pressure is about 0.7 megapascals, and our air tank stores up to like 27.6 megapascals. So yeah, that's just the specs on those.